moment, that information, the history of every particle, is the most sacred law in the cosmos. It can't be created, and it can never, ever be destroyed.
It's a core principle. You can change it, you can scramble it, you can hide it, but you can't delete it.
Right. So if you take a book, a big, heavy one, and you toss it into an industrial furnace, you obliterate it, it's gone.
Well, the book is gone, yes, but the information isn't. This is the crucial point. It's a property we call unitarity in quantum mechanics, and it's bedrock.
So what you're saying is the information that made up the book, the specific arrangement of ink and paper, is now just somewhere else.
Exactly. It's encoded in everything that came out of that fire. It's in the chemical bonds of the ash, the exact momentum of the smoke particles, the specific wavelength of every photon of heat and light that was released.
So theoretically, if you had a powerful enough computer, you could capture every single one of those particles.
Every last one.
And you could run the film backward, reconstruct the book from the smoke and ash.
Precisely. The process is reversible. The history is preserved. It's just messy. Very, very messy. But it's there. This is the foundation of everything we understand about quantum reality.
But then we come to the black hole, and the black hole commits a crime that makes burning a book look trivial.
It's a crime on a cosmic scale.
Because when that book falls into a black hole, and that black hole eventually evaporates, the evidence suggests the history isn't just scrambled into the smoke.
The smoke itself is deleted. The information is erased from the universe. It's not just that the book is gone, it's that the very atoms that made it up are scrubbed clean of their past.
And this is the paradox, the black hole information paradox. It's a direct conflict between our two greatest theories of reality.
It is. It's a zero-sum game. You have general relativity, which describes gravity and the smooth fabric of space-time, and you have quantum mechanics, which governs information and matter. And at the edge of a black hole, they go to war. One of them has to be wrong.
And this isn't some academic debate. This is an existential crisis. If information can be destroyed, then our entire understanding of reality is built on a lie.
The stakes are, quite literally, everything. We are forced to choose. Does the beautiful, predictable geometry of Einstein's universe break down at the edge of a hole? Or do the quantum laws that protect history simply fail? Something has to give.
To really feel the weight of this, we have to start with the classical picture. The perfect suspect. We have to build Einstein's fortress before we watch the quantum siege.
That's essential. Before the indictment, the black hole was seen as this perfect geometric object. Carl Schwarzschild gave us the first solution to Einstein's equations, and it described a prison.
A prison with no walls.
Exactly. A prison made of warped causality, a region of spacetime so twisted that even light can't find the exit.
And the boundary of that prison is the event horizon. For decades, this was just seen as a mathematical line in the sand, right? A point of no return.
And its perceived perfection, its smoothness, comes from one of the absolute pillars of general relativity, the equivalence principle.
Which says that falling is the same as floating.
Locally, yes. If you're in a free-falling elevator, you feel weightless. You can't distinguish it from flowing in deep space. The consequence for a black hole is the no-drama condition.
So our astronaut Alice is falling towards the horizon. What does she feel?
Nothing. She feels absolutely nothing. There's no signpost, no jolt, no wall of heat. She just floats serenely across that mathematical line, completely unaware that she's just past the point of no return.
That smoothness is everything. If Alice feels anything at all, a bump, a flash of heat, then the equivalence principle is broken.
And if the equivalence principle is broken, general relativity itself is in deep trouble. So in the classical view, Alice and her book of history sail smoothly across the horizon, and the information is now safely locked inside, causally cut off from our universe forever.
It's the perfect hiding place.
The perfect vault.
And what's inside that vault is terrifyingly simple. The no-hair theorem.
It's a shocking loss of complexity. You could take a star made of solid gold, another made of pure diamond, a third made entirely of old books. If they all have the same mass, they form identical black holes.
All that detail. The hair is just shaved off.
Gone. From the outside, a stationary black hole is described by just three numbers: its mass, its electric charge, and its angular momentum. M, Q, and J. That's it. The entire history of a star reduced to three parameters.
That is the ultimate act of cosmic censorship.
And all that lost history, all that information Alice is carrying, is now on a one-way trip to the core.
The singularity. At R equals 0. And this isn't a place, is it? That's the part that's so hard to grasp.
It's not a location you can try to steer around. It's a moment in your future.
A moment in time.
Once you cross the horizon, the roles of space and time literally swap. The direction inward becomes the direction future. Moving forward in time is moving toward the singularity. You can't avoid it any more than you can avoid next Tuesday.
That's horrifying. Your own personal timeline now terminates at a point of infinite density.
Where physics as we know it just ends. So the classical picture is perfect. It's a smooth, simple monster that hides information forever. It's unassailable.
Until 1974.
Right. And of course, real black holes spin. That's the Kerr metric. It's more complex than the static Schwarzschild solution, but it's still perfectly smooth.
And what does that spin do to the space around it?
It drags space-time along with it.
Yeah.
It creates this region outside the horizon called the ergosphere, where space itself is moving so fast you physically cannot stand still relative to the distant stars. You are forced to orbit with the whole.
So it's like being caught in a whirlpool of pure space-time.
An incredibly violent one. You can still escape the ergosphere, but it shows how dynamic the geometry is. And that distortion, that spinning shadow, is going to be the key to everything when we get to the observational tests.
So, to sum up, the classical black hole is a flawless vault. Smooth, simple, and eternal. A perfect crime scene. But then, the quantum detectives showed up. And they showed up with an indictment that threatened to tear down the entire fortress of general relativity. This is the quantum siege, and it begins with a new understanding of empty space.
It begins with realizing that what we were applying was an approximation. It's called quantum field theory in curved spacetime. We don't have a full theory of quantum gravity, so we had to compromise.
What was the compromise?
Take the spacetime of the black hole as a fixed classical background, that's the general relativity part, and then you let quantum fields, the stuff that makes up light and matter, play on top of that fixed stage.
A hybrid theory.
A hybrid theory. And the first thing that theory tells you is that the vacuum, empty space, isn't empty at all.
Right, the Heisenberg uncertainty principle. It says you can't have perfect nothingness.
Correct. The vacuum is seeding. It's a roiling foam of so-called virtual particles, particle-antiparticle pairs that pop into existence out of borrowed energy.
And then immediately annihilate each other, paying the energy debt back.
Instantly. They flicker in and out of being, too fast to be observed directly. A constant quantum churn.
But near a black hole, that neat little transaction gets violently interrupted.
Violently is the right word. The gravitational gradient, the tidal force at the event horizon, is so extreme that it can physically rip one of these virtual pairs apart before they can annihilate.
So one gets pulled in and the other escapes.
That's the key. One particle, through a quantum tunneling effect, escapes out to infinity. It becomes a real particle that we can detect. We call it Hawking radiation.
Right.
But for it to become real, it has to have positive energy.
Okay, that makes sense. But energy has to be conserved.
Always. So if the escaping particle carries away positive energy, its partner, the one that falls into the black hole, must carry negative energy.
Whoa, hold on. Negative energy. That sounds like science fiction. What does that actually mean?
It's a profoundly weird concept. The best way to think about it is as a mass debt. When the escaping particle was promoted from virtual to real, the energy had to come from somewhere. It came from the black hole's gravitational field. The infalling particle is the IOU. It carries that debt into the hole.
So when this negative energy particle hits the singularity, it doesn't add mass to the black hole.
It subtracts it. It's like adding a negative number to the ledger. The black hole's total mass energy goes down.
Which means black holes aren't truly black. They glow.
They glow with the perfect thermal temperature. And here's the kicker. The temperature is inversely proportional to its mass. The bigger the black hole, the colder and slower it radiates. The smaller it is, the hotter it gets.
So a stellar mass black hole would be incredibly cold.
Colder than the background radiation of the universe.
Yeah.
But the principle is what matters. It's a runaway process.
Runaway process.
It radiates, so it loses mass. As it loses mass, it gets smaller. As it gets smaller, it gets hotter. As it gets hotter, it radiates even faster. It's a feedback loop that ends with the black hole completely evaporating in a final massive burst of gamma rays.
And if the black hole vanishes, what happened to the book Alice carried inside? Where did that information go?
That is the $100 billion question. Because the radiation it emits is purely thermal.
Meaning it's random noise?
Perfect, high-entropy random noise. The radiation's properties are determined only by the black hole's mass, charge, and spin, not by what fell in. The radiation from a black hole made of books is identical to the radiation from one made of gold. It carries no memory. No record.
So you start with a star, a highly ordered, low-entropy, pure quantum state,
A known state,
and you end up with a cloud of random high-entropy mixed thermal radiation.
and that is the crime. That is the crisis of unitarity. Quantum mechanics forbids that transformation. You cannot, by any lawful process, turn a pure state into a mixed state. It's like taking a perfectly ordered deck of cards and finding it's turned into a random pile of ash. The rules don't allow it. If this is real, quantum mechanics is wrong.
Okay, so unitarity, the conservation of history, has to be saved. It's too fundamental to throw away. But general relativity says the horizon is a smooth, one-way door. How do you square that circle?
Well, the first major attempt was less a solution and more of a philosophical truce. It was called black hole complementarity.
A truce based on the idea that no single person could ever witness the contradiction.
Exactly. It centers on our two observers again, Bob on the outside and Alice falling in. It argues that what they see can be totally different, and that's okay because they can never compare notes.
So let's take Bob's view. He's watching from a safe distance. For him to see unitarity saved, what has to happen to Alice's book?
For Bob, the information can never cross the horizon. Because of the extreme time dilation, he sees Alice and her book slow down as they approach the horizon, getting stretched and flattened against it.
Like a bug on a windshield.
A very hot windshield. From Bob's perspective, the horizon is a scorching membrane. The information from the book hits this membrane, gets completely scrambled, and is then re-emitted as part of the thermal Hawking radiation.
So for Bob, the book is incinerated on the surface. Information is returned. Unitarity is saved.
Correct. But now consider Alice. She's falling. And for the equivalence principle to be true, she has to experience that smooth, no-drama passage.
So for Alice, there is no hot membrane. There's no wall.
None at all. She floats harmlessly across the horizon, carrying the book and its information with her, completely intact, on its way to the singularity.
So Bob says the information is outside, scrambled, and radiated away. Alice says the information is inside, safe and sound.
And that is a spectacular violation of a fundamental quantum rule, the no-cloning theorem.
You can't have two identical copies of the same quantum information in two different places.
It's strictly forbidden. But this is where the truce comes in. Complementarity argues that since Alice can never get back out to tell Bob he's wrong, and Bob can't jump in to check on Alice without also being trapped.
The contradiction is unobservable, so physics just sort of gets away with it.
It proposes that both realities are true, but only within their own reference frame. It's a deeply unsettling idea that reality itself might be observer-dependent.
It sounds more like a legal defense than a physical theory.
It felt that way to many people. But it was so powerful because it led directly to one of the most profound ideas in all of physics.
The holographic principle.
Yes. If all the information for a 3D black hole can be described by what happens on its 2D surface, as it is for Bob, then maybe that's a general rule.
How did the math work out for that?
It came from black hole entropy, the amount of information a black hole can hold. Normally, entropy scales with volume. A bigger box holds more stuff. But the Bekenstein-Hawking formula showed that a black hole's entropy scales perfectly with the area of its event horizon.
The information capacity is tied to the boundary, not the bulk.
Exactly. The maximum amount of information you can cram into any region of space is not determined by its volume, but by its surface area. One bit of information for every 4 tiny units of area called a Planck area.
And the implication of that is just staggering.
It's mind-breaking. It suggests that our entire three-dimensional universe might be a projection, a hologram. All the information that describes our 3D reality could be fully encoded on some distant two-dimensional boundary surface.
So to save the black hole's memory, we might have to accept that space itself is an illusion. This uneasy truce, complementarity, it held for about 2 decades. It was weird, but it worked. Until 2012, when a new argument came along and just blew it to pieces.
It was a devastatingly simple and elegant argument, known as the AMPS paradox. It showed that complementarity was mathematically impossible, even without Alice and Bob meeting up.
And it relied on another unbreakable quantum law.
A law with a fantastic name. The monogamy of entanglement.
I love that. The monogamy of entanglement, what does it mean?
Exactly what it sounds like. Entanglement is a private, exclusive relationship. If a particle, let's call it A, is maximally entangled with particle B, their fates are perfectly linked.
Measuring one instantly tells you the state of the other.
Instantly and perfectly. But if A is fully entangled with B, it cannot have any entanglement whatsoever with a third particle, C. The relationship is strictly monogamous.
And the event horizon demands a quantum love triangle that violates this rule.
It creates an impossible situation. Let's focus on one of those Hawking radiation particles created right at the horizon. We'll call it particle A. It's just about to escape.
Okay, particle A. Physics places two completely contradictory demands on it.
The first demand comes from unitarity. To save the conservation of information, this newly emitted particle, A, must be entangled with all the radiation that came out before it, which we'll call B.
Why?
Because that's how the information gets out. The outgoing radiation has to be a coherent, pure quantum state, not random noise. That coherence is built on the entanglement between all its parts. So A must be entangled with B to save history.
Demand 1, but then there's demand 2 from general relativity.
Correct. To save the smooth, no-drama horizon, the space right at the edge of the hole must look like a normal vacuum. And what defines a vacuum in quantum field theory is that a particle just outside the horizon, A, is maximally entangled with its partner particle C that is just inside the horizon.
So that AC link is the smooth vacuum.
It's the very definition of it. The smoothness of spacetime is woven from these local entanglement links.
Yeah.
So to save the equivalence principle, A must be entangled with C.
So wait, particle A has to be fully entangled with the old radiation, B, to save unitarity. And it also has to be fully entangled with its partner inside the hole, C, to save the smooth horizon.
And the monogamy of entanglement steps in and says, absolutely not. You can have one or the other. You can't have both.
One of those links has to break.
One of them has to break. And physicists were faced with this horrifying choice. Do you break the link to the outside and kill unitarity? Or do you break the link to the inside and kill smooth space-time?
And the consensus was, you save unitarity at all costs.
At all costs. Which means the link between particle A on the outside and particle C on the inside must be severed.
And what happens when you break the entanglement that stitches the vacuum together?
You release an enormous amount of energy. The consequence is immediate. The smooth, calm, no-drama event horizon is gone.
And it's replaced by
A firewall. A searing, high-energy wall of particles right at the would-be edge of the black hole.
So Alice, in her spaceship, she doesn't flit through.
She doesn't even get close. She hits a literal brick wall of pure energy and is instantly vaporized. The equivalence principle is dead. Space ends violently and abruptly at the horizon. The firewall saves quantum information, but it does so by setting fire to Einstein's theory of gravity.
A firewall is a brutal solution. It feels ugly. It saves the math, but it destroys the elegant geometry of general relativity. So naturally, people started looking for even more radical ways out, ways to rewrite reality itself.
Exactly. If the problem is the horizon and the singularity, then maybe the solution is to just get rid of them. The first major attempt comes out of string theory. It's called the fuzzball paradigm.
The idea here is that there is no empty black hole. The event horizon we see isn't a magical one-way membrane.
It's not. The idea is that in string theory, fundamental particles aren't points. They're tiny, vibrating strings. When you try to crush a star's worth of matter down to a singularity, these strings, they resist. They can't be compressed to a point. They puff up.
They fluff up.
They fluff up. They fill the entire volume that the black hole would have occupied, all the way out to the would-be horizon. So you don't get an empty void with a point of infinite density at the center.
You get a ball of string.
A giant, tangled, fuzzy sphere of strings. A fuzzball. Some call it a planet of strings. It has a physical surface, but no inside, no singularity, no place for information to get lost.
Okay, so if it has a physical surface, how does that solve the paradox?
Because there's no horizon to cross. When Alice's book falls in, it doesn't pass through a smooth membrane into a hidden region. It hits the fuzzy surface of the fuzzball.
So it's just like the burning book again?
It's exactly like the burning book. The information gets scrambled into the complex vibrations of all those strings on the surface, and it's eventually radiated back out. Unitarity is perfectly preserved. There's no firewall needed because there was never a smooth horizon to begin with.
A very clean, if bizarre, solution. But there's a competing idea from the other major camp in quantum gravity.
Yes, from loop quantum gravity. This is the Planck star.
And the core idea here is that space itself is made of pixels. It's quantized.
It's made of discrete, irreducible loops. Space-time is not a smooth sheet. It's a fabric with a weave. And that means you can't compress something infinitely. There's a minimum possible size, a maximum possible density, called the Planck density.
So when a star collapses, it can't form a singularity. It hits a wall.
It hits the fundamental quantum limit of compression. And at that point, a new repulsive force from the quantized geometry kicks in, and the collapsing matter bounces
It rebounds.
instantly. For the matter itself, the entire collapse and rebound takes microseconds. It gets crushed to Planck density and immediately explodes outward.
We see black holes that are billions of years old. They aren't exploding.
This is the genius of the model. It
Why?
combines the quantum bounce with Einstein's time dilation. For the star, the bounce is instantaneous. But for us, watching from the outside, that microsecond-long event is stretched by the immense gravity to last for billions or even trillions of years.
So what we see as a stable black hole is actually a star that is in the process of bouncing in extreme slow motion.
That's the idea. It's a timed explosion. The black hole is just a temporary phase. Eventually, after eons, the bounce will complete from our perspective, and the object will effectively become a white hole, the time reverse of a black hole, and release all the information it held.
And this model makes a testable prediction, right, about things we see in the sky.
Potentially. Very old, small, primordial black holes from the early universe should be exploding right about now. And this signal from those explosions, the energy and duration, matches up tantalizingly well with mysterious signals we detect called fast radio bursts, or FRBs.
So these unexplained flashes of radio waves from across the universe could be the death cries of ancient black holes.
It's a speculative but incredible possibility. If we can match the FRB data to the Planck star predictions, it would be stunning evidence for this picture of reality.
Okay, so we have the fuzzball, a string planet, and the Planck star, a time bomb. And then there's the newest, most abstract idea of all, the island.
The island proposal it's a different beast entirely. It came from trying to just get the math right for information conservation to reproduce something called the page curve without explicitly invoking a firewall or a fuzzball.
How does it work?
It's based on a deep connection between gravity and quantum entanglement. The calculation shows that as the black hole evaporates, the quantum information of the outgoing radiation suddenly includes a new disconnected piece of spacetime,
An island.
the so-called island, which is a region inside the black hole's event horizon. It's as if the radiation cloud far away suddenly lays claim to a piece of the interior.
How can a cloud of radiation own a piece of a black hole billions of miles away?
Through wormholes. The mathematics only works if you allow for connections, these replica wormholes that link the black hole's interior directly to the radiation cloud outside.
So spacetime is non-local.
Profoundly non-local. The implication is that, in a quantum sense, the interior of the black hole is the same place as the radiation far away. The information never had to escape because it was already part of the exterior system through these wormhole connections.
That just breaks my brain.
It breaks everyone's brain. It saves the smooth horizon for Alice, but it does so by sacrificing the very notion that here is different from there. To save unitarity, we might have to accept that space-time is stitched together in ways we can't perceive.
This has been an incredible theoretical battle for 50 years. But it's finally moving out of the realm of thought experiments and onto the telescope. We're actually building the tools to get a verdict.
We are. The battleground is the black hole's shadow. The Event Horizon Telescope, the EHT, gave us that first iconic blurry orange donut image of M87. That was the proof of concept.
But the next generation is what really matters here, the NEHT.
The next generation Event Horizon Telescope, it promises the resolution we need to see the fine details of the light right at the edge, to probe the very structure of the horizon itself.
So what does the classical theory Einstein's smooth spinning Kerr black hole predict? We'll see with that kind of resolution.
It makes a very specific, sharp prediction. We should see the main bright ring of light, called the photon ring, but nested inside that, we should see an infinite series of sharper, thinner subrings.
An infinite hall of mirrors.
A perfect description. These are photons that have orbited the black hole multiple times before escaping to us. The N1 ring is light that's gone around once, the N2 ring twice, and so on. The exact shape and brightness of these rings are precise predictions of general relativity.
So if we see that perfect, infinite stack of rings, Einstein wins. The horizon is smooth.
The classical picture holds. But if the fuzzball idea is right, we should see something very different.
Because a fuzzball has a physical surface. It's not a smooth abyss.
It has a texture. It has a quantum fuzziness at its surface, and light trying to orbit that kind of object won't orbit cleanly. It will scatter. It will be disrupted.
So the smoking gun for quantum gravity for the fuzzball would be what?
The higher order rings, the N2, N3, and so on, should be heavily suppressed or blurred or broken. They shouldn't be the perfect sharp rings Einstein predicts. Seeing a fuzzy or broken ring system would be the first direct observation of the quantum texture of spacetime.
We're literally building a camera to see if reality is smooth or pixelated.
That is exactly what we are doing. The fate of these multi-billion-dollar theories rests on the sharpness of a shadow thousands of light years away.
And amazingly, some of the exotic physics needed for these theories is starting to pop up in labs on Earth.
It's an incredible development. In condensed matter physics, in certain very exotic materials at ultra-low temperatures, they've detected excitations that behave exactly like graviton,
The quantum particle of gravity.
the hypothetical quantum of gravity. These chiral graviton modes show that the mathematics of quantum geometry and entanglement can naturally give rise to gravity-like behavior. It's a proof of principle. It shows that the seemingly bizarre physics of fuzzballs isn't just fantasy. It has a tangible connection to real quantum systems. So we come back to where we started. This paradox, this war at the edge of a black hole, has forced physics to a breaking point. We can no longer hold on to all of our cherished beliefs.
Something fundamental has to give. The firewall sacrifices smooth spacetime. The fuzzball and Planck star sacrifice the very existence of the classical black hole. The island proposal sacrifices locality.
Every solution comes at a tremendous cost. But they all point in the same direction. They all tell us that unitarity, the conservation of history, is probably the law that holds. And it's the smooth, continuous nature of space and time that must be abandoned.
It's forcing us to accept that space and time aren't the fundamental stage of reality. They're built out of something deeper.
They're not the canvas. They're the paint. They're woven from the threads of quantum entanglement.
Which brings us to a final, deeply unsettling thought. The most successful solutions to this paradox, holography, fuzzballs, islands, they all converge on one radical conclusion.
That the three-dimensional space you are in right now is an emergent property.
It's a construct, a projection. The smooth, predictable world we experience might be nothing more than the macroscopic effect of countless microscopic quantum bits entangled with one another, like pixels forming an image on a screen or threads woven into a fabric. The black hole is the one place in the universe where the gravity is so strong it tears a hole in that fabric, forcing us to see the stitches and making us wonder if the solid reality we inhabit is nothing more than a hologram.